All right, so this is for Math 160, Unit 2, Part 6. And we are looking at polynomial and rational inequalities. And then the second half of this video, we will be looking at the vertical line test, horizontal line test, and one-to-one functions. So the first half, we will definitely be doing more algebra where we're factoring and solving and then working with inequalities. The second half will be more looking at graphs. So when we're working with polynomial inequalities, that's where we have a polynomial on one side, an inequality sign, and then 0 on the other side. And it can be set up with any of the four inequalities. The roots of the polynomial are going to be called boundary points. And the first thing that we want to do is to set this up so that it is equal to 0 or has 0 on one side. And then we're going to be solving the equation for the boundary points or the roots. We'll then place the boundary points on a number line, and then that'll divide it into intervals. We'll choose a test value within each of those intervals and evaluate f at that number. And then we'll determine whether it's positive or negative on each of those intervals. And then depending on whether we're looking for where it's positive or where it's negative, that'll be our answer. And then we'll write our solution set in interval notation and typically also graph our inequality. So that's what we're looking at in these first few examples. And this first example, we have a polynomial where it is not set equal to 0 right away. So the first thing we need to do is get this set equal to 0. So I'm going to go ahead and subtract 15 from both sides. We have 2x squared plus x minus 15 is greater than 0. And I'm glad the color kind of changed there. It was looking kind of yellow, but now the paper looks white again. So next from here, what we want to do is now that it's set equal to 0, we will go ahead and use the x method or however you prefer to factor. And we'll factor this. So 2 times negative 15 is negative 30, and then 1 on bottom, 6 and negative 5 multiply to negative 30 and add to 1. So 2x plus 6 and 2x minus 5 greater than 0. Take out the trash, and then we have x plus 3 and 2x minus 5 greater than 0. So setting those equal to 0, we get x equals negative 3 and x equals 5 over 2. And from there, we would go ahead and set up a number line, plot those points, and then we're going to choose a test value in each of those intervals. So I'm going to choose something less than negative 3. It could be negative 1,000,000, negative 1,000, negative 10, it could be negative 4. Just needs to be something less than negative 3. And then I want something between negative 3 and 5 over 2. Could be negative 2, negative 1, could be 1, could be 0. And then I need something bigger than 5 over 2. It could be 1,000,000, 1,000, 10, doesn't matter. I'm going to choose 3. You're picking those values. So they're arbitrary values. They're random. It's just whatever you're picking as long as it's less than negative 3 and between negative 3 and 5 over 2 and bigger than 5 over 2. And what we're going to do is we're going to plug these values back into the original function, either where it's greater than or equal to 0 like this, or greater than 0 in factored form. I like factored form better personally, but either one is fine. And so I'm plugging these values back in, and I'm determining is it positive or negative. I don't actually care what the value is. I only care whether what I plug in is either positive or negative. So plugging in negative 4 plus 3 is negative 1. Negative 4 times 2 is negative 8. Negative 8 minus 5, that's negative. A negative times a negative is a positive. Next one, plugging in 0. 0 plus 3 is 3. 0 minus 5 is negative 5. A positive times a negative is a negative. Plugging in 3. 3 plus 3, it's positive. And 2 times 3 is 6 minus 5 is positive. So positive times a positive is a positive. Again, I don't care about the value, I just care about whether it's positive or negative because we chose these values randomly. You could have chosen different values than me. So we only care whether what we get is positive or negative, and that means everything in this interval will be positive. Everything in this interval will be negative. Everything in this interval will be positive. Now, the equation is set up, or the inequality is set up to where we want where this is greater than 0. That means where it's positive. If it had been less than 0, we would be looking for where it's negative. But since it's greater than 0, we're looking for where it's positive, and it's positive right there. So, graphing my answer, negative 3 and 5 over 2. It doesn't have the equal to sign, so I'll have open circles at both of those dots, and I want where it's positive, and that's over here. and over here. And then writing my answer in interval notation, negative infinity to negative 3, parentheses because open dot, and then 5 over 2, again, parentheses, open dot, to infinity. And that's my answer. Now, doing this with rational inequality is basically the same. There's just one other thing we have to consider, and that's that we can never divide by 0. Anytime we have a fraction with variables in the denominator, we need to be remembering that we can never divide by 0. So, first thing we want to do is get it set equal to 0 and have this side be one fraction. And then we're going to set the top and bottom equal to 0. Those will be our boundary points. And then we'll plot these values on a number line. Choose a test value just like we did before, and then write our solution set and graph. So looking at this example, first thing I notice is it's not set equal to 0, so I first need to subtract 2 over. So right now I have two separate terms here. I need to combine this so it's one fraction. So I'm going to multiply by x plus 3 over x plus 3 here to create a common denominator. And that gives me x plus 1 over x plus 3 minus 2x plus 6 over x plus 3. I just distributed the 2. Greater than or equal to 0. And then subtracting. So then distributing that subtraction here, we have x minus 2x is negative x, 1 minus 6 is negative 5, and then x plus 3 on the bottom. And now setting the top and bottom equal to 0, negative x minus 5 equals 0, and x plus 3 equals 0, x equals negative 5, and x equals negative 3. So we're going to go ahead and plot those values on a number line, and then I need to choose a test value in each interval. Well, between negative 5 and negative 3, I'm just going to choose negative 4. Something greater than negative 3 would be 0, and something less than negative 5 would be negative 6. And plugging those into the original, this expression here where it's greater than 0, or set equal to 0, plugging in negative 6 times the negative is positive 6 minus 5 is a positive, negative 6 plus 3 is a positive divided by a negative is a negative. Plugging in negative 4 times a negative is negative 1, is 4. 4 minus 5 is negative 1, and then negative 4 plus 3 is negative 1, and negative divided by a negative is a positive. Plugging in 0, that goes away, a negative divided by a positive is a negative. Now in this expression, again, it's greater than or equal to 0, so we want where this is positive. Okay, so that's going to be my answer then, from negative 5 to negative 3, shaded in between, but we have to be careful here. Even though it has the equal to inequality, we would typically use closed dots here, but what we're actually going to have to do is we're going to go ahead and use a closed dot on 5, negative 5, because that makes our our numerator 0, and that's okay. But negative 3, if I plugged it in, that would make my denominator 0, and I can't have that. So we'll have to use an open dot there, even though it has the equal to inequality. And then writing this in interval notation, negative 5, negative 3 in a parenthesis there. So that is our example of a polynomial inequality and a rational inequality. We're going to go ahead and move on here to inverse functions. And this is kind of a totally different topic than what we were just looking at. Don't, have this expectation that these will look similar or that they're tied together. These are really two separate topics here. And inverse functions, we've been working with inverses and you've seen it before in math. Typically we refer to like multiplicative inverses. So for example, if I have 1/5, the multiplicative inverse of that is 5, because when you multiply those, you get 1, okay? Or additive inverses, where we have, let's say, negative 3 plus 3, that equals 0. Those are additive inverses. So multiplicative inverse, additive inverse. We're going to be looking at inverses of functions now. And this is where the domain and range switch, okay? So remember, what makes something a function? We talked about this earlier in this chapter. We looked at it in Unit 1 as well. That means where each value, x value, matches with only one y value, or each input matches with only one output, or x's don't repeat. So the first thing we're going to do here is just kind of practice again whether something is a function or not. And looking at this first example here, 3 matches to 4, 5 matches to 4, -2 matches to 3, and 7 matches to 1. None of the x values are the same, matching to different y values, so this is a function. The next example, I have 4 matching to 2, 5 matching to 7, -3 matching to 2, and 5 also matching to -1. So the fact that the same x value matches to 2 different y values makes this not a function. Okay. Now, that's how we do it with a set of points, but if we have an equation, the way we can determine whether something is a function or not is by kind of testing the values and seeing if we get 2 outputs. So for example, if I plug in 5 for x, 5 times 2 is 10, plus 1 is 11. It's not like I got 11 and -11. I only got one answer. If I plugged in -3, -3 plus 2 or times 2 is -6, -6 plus 1 is -5. It's not like I got -5 and +5. So yes, this is a function. However, in this next example, almost every x value I plug in fact, there's only one that I can plug in that won't give me 2 answers, gives me 2 answers. If I plug in 4, the square root of 4 is 2, and I get +2 and -2. So I got 2 different answers for one x value. The only x value that doesn't happen for is if I plug in 0, because there's no positive and -0. So no, this is not a function. Okay. Now we're going to be looking at graphs for quite a bit here, and if you recall back to Unit 1, we learned the vertical line test, and this determines whether a graph represents a function or not. And the way we can determine that is if we draw any vertical line through the graph, if it hits more than once, then it's not a function. If it only hits once or it doesn't hit at all, then it is a function. So here, if I draw any vertical line, and again, it only takes one vertical line to make it fail, but every single vertical line I could draw only hits my graph one time. So that means that this, yes, is a function. Okay, so it says, do the following graphs represent functions? Yes, this one is. But this one here, even though lines over here are okay, line right at the vertex is okay, this line here hits it more than one spot. So that means no, it's not a function. This one is a very unique case in that every line is fine over here, but this one single vertical line, not only does it hit more than once, it hits at every single point, infinitely many points. So no, it's not a function. This next one here, even though lines over here are okay, right at the edge of that ellipse is okay, but here where we hit more than once, that makes this not a function. Here we have a square root graph, and every single vertical line only hits once. So yes, it is a function. And here this cubic function, every single vertical line only hits once. So yes, it is a function. Okay. So that was the vertical line test. We learned that before. Hopefully that was a good refresher. We're going to also introduce some new notation. We've been using f of x, and if that's what f of x equals, then the inverse of that function would be using this notation here with that little -1. So the way you would read this is inverse f of x. That's the way you would read that. And notice that the domain and range just switched. Here it was 3, 4, 5, 4, -2, 3, 7, 1. Now it's, instead of 3, 4, it's 4, 3. Instead of 5, 4, it's 4, 5. Instead of -2, 3, it's 3, -2, and then 1, 7. The domain and range just switch in finding the inverse of a function. So now we're going to look at the horizontal line test. And what the horizontal line test tells us is whether the inverse of something is a function. So these graphs here that you're looking at all represent some function f of x. And let me go ahead and label them f of x. But what we're going to be asking a question about is about the inverse. Okay? So the horizontal line test is just like the vertical line test, and it tells me whether the inverse is a function. So this is f of x. The horizontal line test tells me is the inverse a function. And because it hits more than once, that horizontal line, inverse f of x is not a function. Okay. Here, even though it fails the vertical line test, we're not worried about that right now. The horizontal line test passes. So inverse f of x, even though f of x is not a function, the inverse f of x is a function. Okay. Here, horizontal lines all just hit one time, so inverse f of x is a function. Here, even though all these horizontal lines are fine, this one's fine, this one horizontal line hits at every single point, so inverse f of x is not a function. And here, vertical, oops, we're not doing vertical lines, horizontal lines, all of them only hit one time, inverse f of x is a function. And here we can see one horizontal line hits more than once, so inverse f of x is not a function. Okay. All right. Now we're going to talk about a special type of function that is called a one-to-one function. What it means is that it passes both the vertical and horizontal line test, meaning every element in the domain matches with only one range, and vice versa, every element in the range only matches with one domain. Again, now it means no x's or y's repeat. Okay. So here we have three graphs, and we're going to determine if they follow or if they represent one-to-one functions. So I'm going to use a couple different colors here. So let's do the vertical line test first. Vertical line test passes. All right, so f of x is a function. Oh, but it fails the horizontal line test. Inverse f of x, that fails that horizontal line test. So it's not one-to-one. Okay. The next one passes the vertical line test, passes the horizontal line test, so it is one-to-one. And this last one fails the vertical line test. I don't even need to check the horizontal line test, although it does pass it, so it's not 1, 2, 1. We can also determine if a set of points is one-to-one. So I can look at a set of points and determine, do my x values repeat? 3, 5, -2, -1? Nope. 4, 7, -1, -3? Nope. So this is 1, 2, 1. Okay. And then the last one are x values. We have 2, 4, 3, and -1. And then my y values, 3, 7, 8, and 0. None of them repeat x's or y's. I could have like it be 2, 2 or 4, 4 or something like that. That's fine. But none of my y's are the same and none of my x's are the same. So this is also 1, 2, 1. All right, we've got a little bit more practice on the next page, and then that'll be the end of this video here. So we're going to look at a little bit of notation here. Now, we've looked at graphs, we've looked at sets of points, but how do we find the inverse if we have an equation? So the short answer here is that we're going to switch x and y and then solve for y. Again, our domain and range switch. This is the original function. This is the notation for the inverse of our function. And then we're going to see an interesting property here that we'll come back to in just a minute. So we're going to do this first example, and then I'm going to come back to this property here. So here we have a set of points. It says find the inverse of the following. So the inverse of this function, again, we're just switching the x and y values. 2, 1, 4, -3, 8, 7, 4, -3. And notice here, these 2 points are the same. This is still a function. 4 matches with -3 and 4 matches with -3. It's not matching with a different x value or y value. It's matching with the same one. So even though this point's listed twice, it's just being repetitive. It's just redundant. It's if -3 matched with a different y value. So the fact that the -3 repeats or the fact that the 4 repeats doesn't make this not a function. Now, if we have an equation, we can find the inverse by switching x and y and solving for y. And so inverse f of x, or inverse of y, is x minus 1 over 2. We can do this if we have a square as well, even if we have a quadratic equation. Switching x and y, subtracting 3, x minus 3 equals y squared. Square root both sides, plus or minus sign. Y equals plus or minus the square root of x minus 3. You could also use function notation. Okay. Now coming back to up here, if you recall back from the very end of Unit 1, we learned function notation. So here we have f of inverse f of x, and then inverse f of x of f of x. So if we plug f of x into the inverse, or if we plug the inverse into f of x, doing that function composition, if you remember back to g of f of x, and if you recall f of g of x. Plugging a function into another function, if we plug the inverse into the original, then it will equal exactly x. It's not that they're just equal to each other, it's that they're both equal to exactly x, and vice versa if we plug them in the other way. So the way we can verify, it says are g and f inverses. Well, what I'm going to look at here is I'm going to look at g of f of x, and I'm going to look at f of g of x. And if both of those equal x, they both have to, it can't just be one of them. If both of them equal x, then that means that these are in fact inverses. So g is 3x minus 6. And I'm plugging in f, which is 1/3 x plus 2. Distributing that 3 times 1/3, that's just x, and 3 times 2 is 6. Minus 6, that equals x. So we're good so far. Now we need to check the other side. F is 1/3 x plus 2. And I'm plugging in 3x minus 6. 1/3 times 3 is just x. 1/3 times 6 is 2. Plus 2 equals x. So what this means then, again, these 3 little dots mean therefore or so, g of x and f of x are inverses. Let's do another example. Here it says, are the following functions inverses? We have g of f of x that we need to find. G is 2x minus 6. We're plugging in 1/2 x minus 3. 2 cancel out here. We just have x. And 2 times -3 is -6. Minus 6 is x minus 12. And that doesn't equal just x. Even though we could see if they both equal the same thing, it doesn't matter. If it's not equal to exactly x, that means these are not inverses. All right, in our last example here, it says determine if the following are one-to-one functions. So again, remember they need to pass both the vertical line test and the horizontal line test. So in this first example here, it fails the vertical line test. I don't even need to check the horizontal line test. No, it's not one-to-one. Passes the vertical line test, but it fails the horizontal line test. So no, it's not. This one passes the vertical line test. It passes the horizontal line test. So yes, it is one-to-one. All right, and that brings us to the end of part 6.